Okay, welcome to Unit 4B. Before moving on from database technology onto learning, we're going to cover one more emerging aspect uh, that goes beyond MapReduce. In particular, we're going to talk about graph-based parallel computing using the Pregel model. If you recall, our guest lecturer talked about various types of graph-based problems which are important, like computing shortest paths and Steiner trees and things like that. Uh, Essentially, what's happening is that for many of these problems, which are quite important in emerging applications, the MapReduce model has some limitations. We discussed some of these in the last lecture, and we'll revise those as we go along. Just let's remember MapReduce one more time. We have a situation where we have mappers, where mappers essentially read the data at random and decide based on your map function which key to sort this data on, and then the reducers get the data sorted by the key that you decided in the map function, and the platform does the sorting, and the reducers essentially process the data for every key in parallel, and then output the data. This is the MapReduce model. So let's revisit some of the challenges and potential solutions that we looked at a while back. Many applications require repeated MapReduce. PageRank will be one example we'll talk about a little bit later. So there are many ways of trying to optimize MapReduce if you have to repeat it many times. One is to make it more efficient by avoiding copying data between successive reduce and map phases. Second is to generalize the model itself by using arbitrary combinations of map and reduce and pipelining of data between them. And the third is a direct implementation of recursion in a MapReduce-like environment. The graph model is one such model, and there are many examples of it, which we'll talk about very briefly also. And then there's another model called the stream model, which is being developed at Stanford. So let's delve into the Pregel model with an example and how we might do it in MapReduce as well as in an alternative graph-based model. The problem that we consider is the matrix vector multiplication. Now, for those of you who have forgotten your linear algebra, a matrix looks something like this, and a vector is a one-dimensional version, whereas the matrix is a two-dimensional array. And when you do matrix vector multiplication, what you're really doing is taking a row and multiplying every element of this row by the corresponding element of this vector, and then summing everything up. So the first element of this product will be minus 1 times 1 plus 2, which will be 1. Similarly, the second element will be 1 times 1 minus 2 plus 3, which will be 2. The third element will be minus 1 times 2 plus 3, which will be 1. And the last will be minus 1 times 3 minus 4, which will be minus 1. Now let's see how one might implement this in MapReduce. Assuming that we have a very large matrix and a very large vector, we would like to do this in parallel. In MapReduce, we'd possibly do it like this. Take each element aij, which is a whole bunch of elements in any order in various different files, and they have to somehow go to some mapper. Once they get the mappers are going to sort these by column of A and row of X. So what that means is that a mapper will emit the key J for aij. If it reads something called aij, it'll emit J as its key, telling it to go to the jth reducer, and for any element of X, it'll just tell the jth element to go to the jth reducer. Obviously, each real reducer has a bunch of j's which it gets, so each reducer will get a bunch of columns of A and a bunch of rows of X. When a reducer J gets all its elements, it computes the partial product Aij times Xj. Since it's getting the values of Aij for every J, it's also getting for a bunch of J's the Xj's for a bunch of J's. It just multiplies them up for every I. In other words, the jth reducer will compute, say if j is equal to 1, will compute minus 1 times 1, 1 times 1, 0 times 2, times 1, 0 times 1, etc. So it will compute everything for this column multiplied by the first element of X. Similarly, reducer number 2 will compute all the multiplications of the second column with the second row of X, and so on. Now, that's not enough because we still have to add these up this way. So the second MapReduce will do the following. It will distribute these partial products, which are now columns. So each reducer has a bunch of columns after they've been multiplied by the appropriate element of X, and distribute it by rows. For example, the partial product Yij in the vector y prime j will get sent to reducer I, and then these will get added up. For example, so the idea is that these now will get distributed by rows. So part of this will go to one reducer, say the first 2 rows, the second 2 rows will go to another reducer, and then they'll get added up over there in parallel. Essentially what we've done, if you think about this carefully, is we have written this matrix vector product as a block multiplication. So for example, you can write A as a bunch of columns or sets of columns. So A1 could be individual columns, or A1 could be a bunch of columns. And similarly, X1 could be an individual element of X, or it could be a bunch of elements of X or rows of X. And if you write this matrix vector product AX as A1, A2 up to AP, where P is the number of processors that we have, and X1 up to XP, and obviously if you have P processors, you'd have to use appropriate bunches of columns of A and rows of X. And then you just do a similar matrix vector multiplication here. It becomes A1 X1 plus A2 X2, etc. And so essentially it's the sum of these partial products. The partial products are exactly what reducer P computes. So the processor P computes this partial product, and in the first phase of MapReduce, in the second phase, they all get added up. Study this carefully because it's kind of important to understand how matrix vector multiplications are done using MapReduce. This is just one way. There are other more efficient ways of doing matrix vector products using MapReduce. But now let's come to a question of how we would repeat this multiple times if we had to do so. And we actually have to do so using in applications like computing PageRanks, but there are problems.